questions 21 through 25 on the 2011 grade 10 AMC 10A. Two counterfeit coins of equal weight are mixed with 8 identical genuine coins. The weight of each of the counterfeit coins is different from the weight of each of the genuine coins. A pair of coins is selected at random without replacement from the 10 coins. A second pair is selected at random without replacement from the remaining 8 coins. The combined weight of the first pair is equal to the combined weight of the second pair. What is the probability that all 4 selected coins are genuine? So we've got 2 that are counterfeit. So we'll just call them fake, I guess. 2 coins that are fake. And then the genuine coins, there's 8 of them. So GG 8 times. Now, our scenarios, this is a very important line here. The combined weight of the first pair is equal to the combined weight of the second pair. So that is going to be taken into consideration. But first, let's just talk about this. What is the ways that we can do this? Our first pair could be either FF, or it could be FG, or it could be GG. Right? Those are the different scenarios possible. The second pair, if the first pair was FF, then those are both gone. So the only possible second pair is a GG. If the first pair is FG, we still have one F left, so it could be FG again. Or it could be GG for the second pair. And then if the first pair is GG, we can have either FF, we can have FG, or you can have another GG. Okay, so these are our scenarios. Now, of these scenarios, which ones are going to match that sentence? The combined weight of the first pair is equal to the combined weight of the second pair. Well, obviously not this one, because they told us in the question that the weight of the counterfeit coins is different. So there's no way that these and these can have equal weight. What about FG and FG? Sure. Those obviously will have equal weight. FG is equal to FG. So this is good. How about FG and GG? This scenario. That scenario is no good because that's not going to have equal weight. Okay, let's turn our attention to this guy. GG and FF, that's not going to have equal weight. GG and FG are not equal, but GG and GG obviously have equal weight. So these are the 2 scenarios that we have to consider when calculating our probability. I'll call this A and I'll call this B. So our probability, write it up here, is going to be that all 4 coins are genuine. So we basically want B to be the numerator. And the denominator, of course, is the total, which is A plus B. So if I can calculate A, calculate B, I'll plug it back here, and then I'm done with my question. Okay, so how do you figure out the probability of A? Well, for FG, first let's talk about this F here. From the 2 F's that are there, I'm going to choose 1. So it's 2 choose 1. And then for the G, from the 8 G's, I want to choose 1. That would pretty much give me the number of ways of choosing the FG. Now, of course, I've got to turn my attention to this guy, and that's going to be a little bit different because 2 of the coins have already been used. So to get F this time, I've only got 1 F left. So from that 1 F, choose 1, like that. And then since this G was already chosen, I've only got 7 G's left. So from those 7 remaining G's, choose 1. And 7, choose 1. So this is, in terms of numbers, 2 times 8 times 1 times 7. And that is 112. And that is A. Now let's turn our attention to B. GG, this guy right up here, to get 1G from 8, it's going to be 8 choose 1, but we want 2 G's. So it's going to be 8 choose 2. That pretty much takes care of this guy. But then we also have to have that one, We've already chosen 2, so only 6 G's are left. From those remaining 6 G's, we choose 2. So that's 6 choose 2. And that's it. That takes care of that one. And that in terms of numbers is 28 times 15. And that is 420. And that's B. So let's plug it in here. 420 over 112 plus 420. And that is 420 over 532. And in lowest terms, that is 15 over 19. And for 21, that would be D. Each vertex of a convex pentagon ABCD is to be assigned a color. There are 6 colors to choose from, and the ends of each diagonal must have different colors. How many different colorings are possible? All right, let's choose a shape. Obviously, the shape is a convex pentagon. And we've got this rule here that any diagonal, if you were to join them, the vertices opposite each diagonal can't have the same color. All right, so let's talk about this. The first scenario is going to be case 1, and that's if you have all colors different. So since there's 5 vertices, you have 5 different colors. Now we've got 6 colors to choose from, so I can put any of those 6 colors here. But in this vertice that's opposite, I can't put the same color, so I can choose the remaining from the remaining 5. This vertice, I can't put the same color as I did here, but I can put any of the remaining 4. Similarly, I can't put the same color, but I can put any of the remaining 3. And here I can't put the same color, so I can choose only one of the remaining 2. So that obviously gives me 6 times 5 times 4 times 3 times 2 different possibilities, and that is 720. So that takes care of scenario 1. The next case is if you have 4 different colors. And if you have 4 different colors, it's a similar conversation, but you've got 5 vertices. So if you have only 4 colors and 5 vertices, how are you going to do that? Well, what you can do is you can put the same color here and here. That will not violate the rule, because only diagonals have to have different colors, but neighboring vertices can have the same color. So I'm choosing 4, and the first color I have fixed as A, right? Some color that I've denoted as A. But from my 6 colors, I've got to choose 4, right? From the 6 colors that are available, I've got to choose 4. So that's 6 choose 4, exactly the way it sounds. And one of those 4 that I just chose is going to be my double color. So from the 4 colors that I chose, I've got to choose 1 to be my double, the color that appears twice. And then now I've got how many choices for the arrangement of the double colors? This is AA, right? But it can also be like this. A can go here, or it can go like this. It can be AA. You see what I mean? Or it could be AA in the sense that you got A here and A here. So if you do that all the way around, you'll see that there's 5 different ways of doing that, right? So for example, it would be AA, A. These are the 5 different vertices, right? You can have either AA like that, that's 1. A and A like that, that's 2. AA like that, that's 3. AA like that, that's 4. Or AA like that, that's 5. And then finally, for each of those, we've got to choose this, this, and that. I've got 3 colors, so I've got 3 possibilities for that, 2 remaining possibilities for this, and 1 remaining possibility for that. So that's the 3 times 2 times 1. So this equals 6 choose 4 is 15, 4 choose 1 is 4, and then we just got 5 times 3 times 2, 6 times 5, which is 30. So we got 15 times 4 times 30, which is 1800. And now we've got finally our last case, case 3, which is 3 different colors. And the calculation or conversation is very similar to case 2. From the 6 available colors, you're going to choose 3. And from the 3 that you chose, you're going to choose 1 as the color that appears 3 times. So that color is going to here, here, and here. Remember, if they're neighbors, it's fine. It doesn't violate the rules. And then now we have to multiply by how many different scenarios. If you have, let's say, in a very similar way, an arrangement like that, you can have 1 scenario there, 2 scenarios like that, 2nd scenario, I should say, 3rd scenario like this, 4th scenario like that, and 5th scenario like this. So we've got, again, very similar to before, 5 different scenarios that those colors can be placed as, the ones that are all same. And then you've got 2 colors left, so 2 possible choices there and 1 remaining choice there. So times 2 times 1. And 6 choose 3 is 20, 3 choose 1 is 3, and then you got 5 times 2, which is 10. So this is 30 times 20, which is 600. So the total is going to be 720 plus 600 plus 1800. So that's 2400 plus 720, which is 3120. So 22, the answer is C. Seven students count from 1 to 1,000 as follows. Alice says all of the numbers except she skips the middle number in each consecutive group of 3 numbers. That is, Alice says 1, 3, 4, 6, 7, 9, and so on. Barbara says all of the numbers that Alice doesn't, except she also skips the middle number in each consecutive group of 3 numbers. Candace says all of the numbers that neither Alice nor Barbara says, except she also skips the middle number in each consecutive group of 3 numbers. Debbie, Eliza, and Fatima say all of the numbers that none of the students with the first names beginning before theirs in the alphabet say, except each also skips the middle number in each of her consecutive groups of 3 numbers. Finally, George says the only number that no one says. What number does George say? So there's some good news in this question. We don't have to look at everything. That's the good news. I think we only have to look until Barbara, and that should be it, because otherwise Candace, Debbie, Eliza, Fatima, which is the correct pronunciation, it would take absolutely forever, and you have like 3 minutes on this contest to do each question. So first let's talk about Alice, and we'll talk about Barbara, and I think that should be it to figure out George and looking at the answer choices. Okay, so Alice only is going to say 1, 3, and so on, right? So 1, 3, 4, 6, 7, 9, like that. So the numbers that she's not saying are 2, 5, 8, 11, 14, 17, 20, 23, and so on, right? You get the idea. Well, first and foremost, let's talk about Alice. Let's talk about the nature of these numbers. These numbers that she says are either multiples of 3, like 6, 9, 3, 6, 9, or they're of the form 3m minus 2, like 1, for example, is 3 minus 2, or 4 is 6 minus 2, and so on. So these are the numbers that Alice says. So since she says them, George cannot say them, right? Well, 37, one of the answer choices, is of the form 3m minus 2. in particular, when m is equal to 13, I believe, right? 13 times 3 is 39, minus 2 is 37. So that 37, Alice is saying that. So George can't say it. So very quickly, you can eliminate 37. Now let's talk about Barbara. Barbara is saying these numbers, right? But be careful, because she also skips the middle number. So she's only saying 2 and then 8. And then she's saying 11 and 17. And then she's saying 20 and 26. She's skipping over the 5 and the 14 and the 23. Okay? Just be careful about that one. So what form are the numbers that she is saying, the ones that I've circled? Well, they're of the form 2 plus 9n, 2, 11, 20, and so on. And they're also, some of those numbers are of the form 8 plus 9n, 8, 17, 26, and so on. So let's look at the other answer choices. 242. Let's look at this guy right here. 242 is of the form 8 plus 9n. In particular, 242 is of the form 8 plus 9 times 26. So because it is of that form, it is already being said by Beatrice, or Barbara. So since Barbara has already said it, George can't say it, because George is only going to say that number that no one has said yet. Let's keep going here. 365. Is 365 of that form? And it's not, right? If you subtract 8 and divide by 9, you don't get an integer. Now let's talk about 728. And the good news there, it's also of this form, 8 plus 9n. It's 8 plus 9 times 80. 9 times 80 is 720. 720 plus 8 is 728. So since Barbara says that, George can't say it. Now let's talk about 998. 998, I believe, is also of that form. It's 8 plus 990. And 990 is divisible by 9. It's 9 times 110. So since Barbara says 998, George can't say it. So there you go. By process of elimination, 365 is the number that George says. And that saves us a lot of time. We don't have to go through Candace, Debbie, Eliza, and Fatima. So number 23, the answer is C. Two distinct regular tetrahedra have all their vertices among the vertices of the same unit cube. What is the volume of the region formed by the intersection of the tetrahedra? Here's a very helpful diagram to sort of better understand the three-dimensional aspect of this question. The tetrahedra is split, as you can see. There's two of them, right? There's one that has this vertice, that vertice, and that vertice, and that one. And then the other one has these three vertices, and then of course a vertice that you can't see that's behind. And when you draw it like this, you can see that it chops off, right, segments. And the good news is that those segments are exactly 1/8 of the total volume. So the tetrahedra is split into 8 smaller tetrahedra. And we have the responsibility of figuring out the volume of the region formed by the intersection of those two. So what is the region that's common to both? And 4 of these 8 smaller pieces are common to both. I hope you can see that. Let's see if I can illustrate that. Like, for example, this segment, that's 1, and this segment is 2, and this segment is 3. You'll notice those 3 are not part of the other tetrahedron that they have shaded. And then there's going to be another 4th one behind that you can't see. So those 4 will not be part of the other shaded tetrahedron, but then there's 4 other small pieces that will be, right? So that's why it's 4 and 4. So 4 of those smaller pieces are inside and 4 are outside. So our task is to figure out the volume of the tetrahedra. And since 4 of the 8 are inside in the region that's makes up the intersection, basically half of the volume is in that region. So what we are going to do in this question is first figure out the volume of one of those tetrahedra, and then the region that is formed by the intersection is half of that. It's 4 out of the 8 smaller identical tetrahedra. And once we get this value, that will be the answer to our question. Okay, so that's the strategy. So here we go. Now, each of these tetrahedra, you'll notice, have this sort of as their, I guess you can call it the base, right? And very quickly you can figure out, since this is a unit cube, right, they tell you that these sides are all 1, 1, like that. So this hypotenuse, you can immediately calculate as root 2. So this is root 2, that's root 2, like that. Okay? So it's a tetrahedron with root 2 for the sides of that equilateral base, and then there's going to be some height. And then eventually, of course, we have to figure out the height of that tetrahedron in order to calculate the volume. So the height will be that red line, and I will be able to calculate that using Pythagoras, since this is going to be a right angle. Okay, so let's calculate the volume. What is the volume of a tetrahedron? It's 1/3 times the area of the base times the height. So I think this is the easiest way of remembering that. Let's concentrate first on the area of the base. And the area of the base is just the area of an equilateral triangle. So here's an equilateral triangle, and we have previously concluded that it has sides of root 2. So let's find the area of this first. The area of an equilateral triangle, of course, we can find with just that 1/2 base times height. So 1/2 base times height, and the base in this case obviously is root 2. So it's 1/2 times root 2, but we need the height of this guy right here. Don't get confused with this height. That's the height of the tetrahedron. This h that I drew in here, which I guess I'll just write small h, that's the height of the base. So it's like from here to here, I guess. Okay, well, this is a 30, 60, 90 triangle. So this is obviously 60 degrees. And this is 30. So using the ratios of 1, 2, and root 3 for the ratios of the sides, I can calculate h. H, therefore, will be h over root 2 is equivalent to root 3 over 2. So that means h is root 6 over 2. So there you go, root 6 over 2. And therefore, the area of the base, we can quickly calculate. It is root 12 over 4. Like that. Okay, so we'll put that in here. 1/3 times the area of the base, root 12 over 4. Now we need the height of the tetrahedron. We need this red line, that one top to bottom. Now how do we figure that out? Well, again, it's going to be Pythagoras, right? If this top to bottom is my big H, height of the tetrahedron, the hypotenuse, this, I've exaggerated a bit. It's a lot bigger than what it actually looks like. But that is going to be just root 2. Since the tetrahedrons, all the sides are the same, they're all root 2. Now, I got to figure out this, though. That one I haven't figured out yet. Okay, let's draw another triangle to avoid making this messy. There we go. And I've got to figure out this distance from here to here. from there to there. Okay, that shouldn't be a problem. Let's divide this equilateral triangle into segments. That will allow me to figure that out by drawing perpendiculars like that. And that segment is the equivalent of this segment right here. From here to here. So I can do that pretty simply with the 30, 60, 90 again. This is 30, this is 60, and as always the ratio is 1, 2, and root 3 for the sides. And then from here to here, that is half of root 2. And I guess this red that I'm interested in, I'll just call it x. So therefore, x over root 2 over 2 is the same as 2 over root 3. So that means x is equal to root 2 over root 3. So now I can go back and label that x, and I can figure out h now using Pythagoras. So h squared plus x squared is root 2 squared. So h squared, x squared is going to be root 2 over root 3 squared, so that's just going to be 2 over 3, and this is 2. So h squared is 2 minus 2/3, and that is 4 over 3. And therefore h is just going to be the square root of that, which is 2 over root 3. So there we go. We got the final piece of the puzzle, and now we can figure out the volume. So this volume looks like, let's see here. We've got 2 and 12 and the numbers, and then root 12 over root 3. Well, that's just 12 divided by 3, which is 4, and then square root of 4, which is 2. So that looks like 4 over 12, which is 1 over 3. And then I kept this in the screen for a reason, and as I had explained before, once we get the volume, the amount of that is in the region that is common to both tetrahedra, if you want to review it, the volume of the region formed by the intersection of the tetrahedron, if you remember, it was 4 out of the 8 small tetrahedra. So basically half of the volume is in that region formed by the intersection of the tetrahedra. So half of that volume is the answer to our question, and half of V is 1/2 times 1/3, which is 1 over 6. So the answer to number 24 is D. Let R be the square region with n greater than or equal to 4, an integer. A point x in the interior of R is called n-ray partitional if there are n rays emanating from x that divide R into n triangles of equal area. How many points are 100-ray partitional but not 60-ray partitional? Let's first discuss what this question means. So we'll draw a diagram. Here's a square. And what I'm going to do is putting it on a coordinate grid. And we'll just put some point we can call x. So right here, let's say that's x. And emanating from x, you're going to have these rays, right? And obviously these rays are emanating in such a way that they divide that square into a whole bunch of equal triangles. So some of those rays obviously will need to go through the vertices. So let's just draw those ones that go to the vertices like that. Then we've got another one going down here, and then another one going to that. Okay. Now this one, of course, as you can clearly see, it divides it into 4 regions, and these 4 regions are not equal, but there's going to be a whole bunch of rays that emanate in order to make a whole bunch of equal segments. So that is the challenge of the question, right? I'm just, in a very sloppy way, sort of just showing you that all of those segments eventually are going to have equal value. But we don't know how many there are for the general case. We're given two cases, 60 and 100, but obviously we're not going to draw 100 of those emanating rays. That would be impossible on a diagram. So we have to talk about it in terms of general terms. So here we go. Make things easy. Let's put this on a coordinate grid, and let's call this 0, 0. Let's call this point 1, 0. This is 1, 1. And this is 0, 1. Okay? So first and foremost, x, I will give some sort of a coordinate. I'll call it AB. A on the x-axis and y on the b on the y-axis. So if I drop a perpendicular from that point x, and similarly if I extend it to the y-axis, those are obviously going to be labeled here as A and here on the y-axis as B. Okay, so now what we can do is we can label these four regions. This region right here, this guy, I will call R1. So I'll try not to make it confusing. And this region in here, I will call R2. This region here, I will call R3. And the last one, of course, this guy, I will call R4. So let's first calculate the area of all of these. R1 is 1/2 base times height. The base, of course, is just 1, and the height is B. So R1 is B over 2. R2, that is also 1/2 base times height. The base is 1, and the height is from here to here, which is 1 minus A. So that's 1 minus A over 2. R3 is this one, and this height is 1 minus B. So it basically becomes 1 minus B over 2. And finally R4, that's going to be A over 2 in terms of its area. All right. So we have to do a few things here. The first thing is, of course, to understand that R1, R2, R3, R4 are not equal. We have to divide them in a way so that every single divided segment is equal throughout the entire square. So let's now do those divisions. And this region, that's R1, I will divide that into N1 different segments. This region, R2, I'll divide into N2 different segments. This region, I'll divide into N3 different segments, and this region, N4. So essentially what that means is that you're going to draw N1 different emanating rays to cut that into equal segments. Okay, I don't know how many N, but N is obviously a lot. And in a very similar way, you have to do the same thing with R2. You have to draw N2 different lines. So whatever, if N2, let's say it was 20. And the goal, of course, is that, and it says in the question, that divide that square into triangles of equal area. So that's the goal. So we'll talk about this bit by bit to explain it. So that means once you cut all of those into segments, those segments are all equal. Okay? And that's very important to understand. So that means that B2, when it's divided by N1 segments, each of those segments is B2N in terms of its area. And then similarly, when you do that with R2, each of those segments is 1 over A over 2N2 in terms of its area. And then very similarly for R3, it's 1 over B 2N3. And then for R4, it's A over 2N4. So each of these is equal to each other. So all of these are equal. Okay, so I hope that makes sense. Now, since we've got this equality, let's use it. And in particular, let's use the ones that have the same variable, at least for A and B. So B over 2N plus 1, 2N1 is 1 minus B 2N3. And this will allow me to isolate for B. Cross multiply and you get 2. Actually, let's get rid of the 2's first. So I will only need to cross multiply B with N3. And then this will become N1 minus B N1. Put everything on one side and you get B N3 plus N1 all over is equal to N1. And therefore B is equal to N1 over N3 plus N1. Okay, so that's going to be very helpful for us. And in a very similar way, let's equate those two. And when you do, you get 1 minus A is over N2 is equal to A over N4, right? I just got rid of the 2's. And cross multiply A and 2 is N4 minus N4A. And then bring the A's over and you get A N2 plus N4 is equal to N4. And then finally, A is equal to N4 over N2 plus N4. Okay, so far so good. I hope this you have been following without too much confusion. All right, now this is a very important part of the question. Look back up here, R1 and R3. If you were to add them, right, R1 plus R3, what do you get? You get B over 2 plus 1 minus B over 2, and that is equal to 1/2. Now the area of the entire square, it's a unit square, which is what I chose to make this easy in terms of the math, has an area of 1. So R1 plus R3 are essentially half the area. Very similarly, look at R2 plus R4. This and that. If you look at those and add them up, it's 1 minus A over 2 plus A over 2, and that is also a half. So that means those two regions comprise a half. And that's very important because that means that, and I'll try to explain this carefully, in R1 you have N1 triangles, right? Because N1 rays are going to be emanating from X, whatever N1 is. So you're going to have N1 triangles in R1. Similarly, for R3, you're going to have N3 triangles because you're going to have N3 rays emanating from X. And all of the triangles that make up R1 and R3 are given by this number, N1 plus N3. That is all the triangles that make up region R1 and R3. And all of those triangles add up to a half in terms of their area. Very similarly, for region R2 and R4, you have N2 plus N4 triangles. And remember, the question told you that all the triangles have equal area. And because they all have equal area, that means these two must be equal. Okay? That's a very important point in the question. I hope that I've explained that well. All right, so now we can proceed. We are told that we want to create 100 partitions. So that basically means that N1 plus N2 plus N3 plus N4 has to equal 100, right? 100 partitions for those 4 regions. Well, that's very helpful. And since n1 plus n3 is equal to n2 plus n4, right over here, that means that we can separate this n1 plus n3 plus n2 plus n4 is equal to 100. And both of these are equal, right? According to this right here. So both of those, if they're equal, they must be equal to 50 each. So that's 50 and that's 50. Okay, so here we go. Let's keep that square in the diagram. So that means my x, which I had previously labeled as AB, and I had figured out that it was, if you remember here, B is n1 over n3 plus n1. And that basically means that it's going to be n1 over 50, since n3 plus n1 is 50. And A was n4 over n2 plus n4. That's basically n4 over 50, since n4 plus n2 is 50. So I've got n1 over 50 and n4 over 50 for my values of B and A. So that's n4 over 50 and n1 over 50. So what that means is that this is a fraction. So x can be anywhere from here to here, right? And for example, if n4 was 25, it would mean that this is 25 over 50, which is a half. So x would have an x coordinate of a half. Does that make sense? Or very similarly, let's say n1 is say 10. That would mean this would become 10 over 50, which is 1/5. That means x has a y coordinate of 1/5, which is approximately here. Okay, so this is very helpful at this point, because that means that n4 can be any integer from 1 to 49. The reason it has to be an integer is because n represents the number of emanating rays, right? It's the number of rays, so it has to be an integer. Why 1 to 49? Why not 1 to 50? Because if it's 50, then it would be right on this line. It would be 50 over 50, which is 1. And x is inside that square. Okay? So for n4, I have 1 to 49 choices. And for similarly, I also have 1 to 49 as my choices for the same reasons. So the number of ordered pairs, I guess, AB, are 49 possible ordered pairs for n4. Well, for 49 possible choices for n4 and 49 for n1. So 49 times 49, which is 2401, is the number of ordered pairs AB. Okay? But remember, this whole conversation is for 100 ray partitions. Okay? We want to compare it to 60 ray partitional. If you have 60 ray for the question, then it would essentially be identical in every way. The only difference is that when you get to the very end, your x would be some sort of m over 30 and some sort of m over 30, like that. Exactly how we got it up here. Everything else would be identical, except for instead of 50-50, it would be 30-30. And our question is saying, how many of these are not going to be like this? So let's compare these to these. Well, we want to compare n over 4 over 50 to m over 4, 30. And if you do the math there, you cross multiply, you get that m4 is 3 over 5 n4. So that means that for any of these values from 1 to 49, the only way you can get an integer for m4 is if the number that you put in for n4 is divisible by 5. So the only way you're going to get integer values for M4 is if you put values for N4 that are divisible by 5. So for example, M4 can only be a integer if you have the following values for N4. 5, 10, 15, 20, 25, 30, 35, 40, and 45. From 1 to 49, these are the only 9 values that will give a integer value. So for example, when N4 was say 20, this would be 20 divided by 4, 20 divided by 5, which is 4. 4 times 3 is 12. M4 would be 12. Okay? Does that make sense? So these are the ones that we cannot have because we don't want this to have any common with that. So first and foremost, how many are there? Well, there's 9 for N4. 9 for M4. 9 values. And very similarly, you'll get 9 for M1. So 9 times 9, which is 81, represents the number of ordered pairs of that form for a 60-ray partitional scenario. So from this 2401, these 81 I cannot have. So I have to subtract from 2401 those 81. So that's the final step to our question. 2401, subtract these 81, because I don't want these to be the same as this, and they will be the same when you have these 81 ordered pairs. And this number is 2320. And that is the answer to the question. 2320, number 25 is choice C.